So next speaker is Johan, and he's going to talk about his CRAM system. So you have to talk. This is your time now.
Hi everyone, my name is Will. My thesis is called A Cable-Driven Remote Access Manipulator with CRAM, and my supervisor is Dr. Arlo. So I have a short video which is just going to give some context to the rest of my presentation. CRAM is a cable-driven remote access manipulator. It is designed for inspection of confined spaces, such as aircraft wing assemblies. To maximize the length to diameter ratio, the system is actuated by a cable-driven mechanism. The system has 5 2-degree of freedom joints, each with bending angles of plus or minus 90 degrees. This allows for highly articulated motion. The main focus of my thesis was how to control CRAM. The first control method is called tip following, allowing confined spaces to be accessed. The second method is tip positioning, to conduct the relevant inspection operations. Both methods pose unique challenges. Okay, so I'm just going to give a quick overview for the rest of the presentation. To start with, I'm going to go over the motivation behind the CRAM system, and then the hardware and the system architecture. And then I'm going to go into the main focus of my thesis, which is the 2 control methods. The first being tip following, and then tip position. So the motivation behind the CRAM system is the need to conduct inspection operations in confined spaces. And the specific confined space I've chosen to focus on is an aircraft wing structure. These arrows show the path that a manipulator would need to take to access the confined space through an access port. And from this path, we can derive some of the system requirements. So these are the need for remote access to the confined space, the need for highly articulated motion, and also for large bending angles of plus or minus 45 degrees. So from these system requirements, I designed a 12-degree of freedom manipulator, which is called CRAM, which stands for Cable-Driven Remote Access Manipulator. And using this as a platform, I could pose a research question for my thesis, which was, what are some of the control strategies required for the control of CRAM in a confined space, such as an aircraft? I developed the 4-degree of freedom prototype, and the main parts of the prototype are the base of the manipulator and the arm part. And what's unique about the design is that unlike a conventional manipulator which has actuators at the joints, all the actuators are placed in the base of the system, and movement is through these steel cables. So here's a close-up of what the joint looks like, and the main part are these pulleys around which the steel cables are around for actuation. And it requires quite high cable tension to reduce the backlash in the cable mechanism. So there's this tensioning mechanism with these tensioning bolts which pull on the cables and tighten them. The actuators are high torque servo motors, and then all the relevant power and control electronics are also placed in the base. Here is a CAD model of what one of the joints looks like, and it's based on the design of the universal joint. So it allows it to have 2 degrees of freedom per joint, and the placement of the pulleys allows it to have plus or minus 90 degrees of freedom per 90 degrees per degree of freedom, and this maximizes the degree of articulation. Here's the system architecture, and it's split into 2 main modules. There's the control module and then the CRAM system. So if you look at the control module, there's a user input via a gamepad which feeds into the high-level control schemes which are running on MATLAB and Simulink on a laptop. And this sends serial data to a microcontroller which is used to interface with a stepper motor which is responsible for linear motion of the base, each of the servo motors which are responsible for bending of the joints, and then there's also encoders placed on each of the joints to account for any backlash in the cable mechanism. This then feeds into quadrature counters and communicate via SPI with the microcontroller, and then those joint angles feed back into the high-level control scheme. So as I said, the main focus of my thesis was these high-level control schemes which are running on the laptop. So the first one, which I developed, is called tip following. And tip following involves the user defining the path that the end effector of the manipulator should take, and then the rest of the arm following as closely as possible. So a commonly used method, I'm calling it the previous pose method, was presented in this paper. And this diagram shows how it would be implemented on the CRAM manipulator. So each one of these dots represents one of the two referring joints. And the way it works is that at each iteration of the algorithm, it moves the base forwards, and this causes the tip to translate forwards. And it runs an optimization where to find the new pose at each iteration, which is shown in black, it compares it to the previous pose, which is shown in blue, and then looks at a number of test points along the new pose and compares it to the previous pose and tries to minimize the displacement. Now, I developed a new method which I'm calling the point cloud method. And the way this works is that at each iteration it stores the position of the end effector, and that's what these yellow dots are. And then it optimizes the new pose by minimizing its displacement from the lines drawn between each of the previous poses rather than from the previous pose. So that's what's called the point cloud method. So this graph shows a comparison of the two methods. So on the y-axis we have the maximum error of the tip following, or the deviation from the ideal path we wanted to take in millimeters. And the x-axis is the number of iterations of the algorithm. And what this shows is that when we use the previous pose method, there's this accumulation of errors, which is not present in the point cloud method. Here's another comparison of the two methods. So again, the y-axis is the deviation from the path, but this time the x-axis is how sharply curved the path is that we want the manipulator to take. And again, the point cloud method outperforms the previous pose method in this regard. The second control method is called tip positioning, and this can be split into two problems. The first is called forward kinematics, which says, if you know the state of each of the joints along the manipulator, can you figure out where the end effector is? So the method I use is called DH parameters, which involves starting at the base of the manipulator and then translating and rotating along until you get to the end effector. Second problem in tip positioning is called inverse kinematics, which is, given an end effector pose, can you figure out how you should arrange all the joints to achieve the pose? This is the equation I use to solve the inverse kinematics. I'm going to explain a little bit about what each of the terms means. So this first term on the right-hand side is like a spring, and it pulls the end effector towards the desired position. The second term refers to the fact that you can move the joints of the manipulator without affecting the end effector. And this is called self-motion, and you can use it to optimize some additional constraint. So for the CRAM implementation, I used it to minimize all the joint angles, so it made them avoid their mechanical limits. Here's the Simulink model of the tip positioning scheme running on the CRAM system. And the main parts of this are the position input from the user, which then feeds into the CRAM subsystem, which communicates with the servo motors and the encoders. There's two feedback loops. This inner feedback loop is to control all the joint angles, and this outer feedback loop uses the forward kinematics to have a feedback loop of the tip position. And these blocks show where these parts of the equation are calculated. So the results of this tip positioning scheme are shown in this diagram. This shows it running on the 4 degree of freedom prototype. And this is the Z, Y, and X position in millimeters of the end effector. And these dotted lines represent the desired position that I input. And what this shows is that as the control method is running, it effectively causes the pose of the end effector to converge to the desired pose. So the main limitation with this method is what's called kinematic singularities, and this is best explained using what's called a velocity ellipsoid. So for this manipulator here, this represents the velocity ellipsoid, which is how easy it is for the manipulator to move its end effector in a desired direction. So if we were to pull on it with a spring like this, it's really easy for it to move. But if we look at this case here, this is a kinematic singularity. And what's happened is the ellipsoid is really squished. So if we were to pull on it with a spring like this, it would cause the joints to like pop, which creates a lot of instability in our control method, which is really undesirable in these constrained environments where we need really reliable motion. So to solve this, we implement what's called the damping factor. And to implement this damping factor, we need some sort of measure to tell us how close we are to a singular configuration. So these measures are called manipulability measures. And a commonly used measure is called the local conditioning index, which is given by this equation. And the main limitation of this method is that it can't be written as a function of the joint angles. So to get around this, in this paper, they presented a new measure called the measure of isotropy, relatively new, given by this equation. And I developed a new measure which I'm calling the harmonic isotropy measure, which is given by that equation there. And if we look in this graph, you can see a comparison of the methods. So this y-axis is the output of each of these equations, and moving along the x-axis to 0 represents approaching a singularity. So each of the measures gives 0 at a singularity, but what we're concerned with is what does the measure output near a singularity? So if we look at the zoomed in and rescaled portion of the graph, the low conditioning index in blue and the measure of isotropy in red both dip down as you get to 0, whereas the new measure in yellow becomes linear. So it's a really good measure for telling us how close we are to the singularity. And the reason that's important is shown in this graph. So the y-axis here represents how unstable our control method is. And again, moving towards 0 represents approaching singularity. So the purple curve represents no damping. So as you can see, it shoots up to infinity and becomes unstable. And if we compare using the previous two methods, damping with the new measure provides much better damping compared to the previous methods. Now we can extend the new measure to include a weighting factor, so it becomes the weighted harmonic isotropy measure. And this allows us to define our desired velocity of ellipsoid for the manipulator. And then we can optimize its pose and achieve super reliable motion in these confined spaces by tuning our damping based on the characteristics that we want. I think I'm probably out of time, so does anyone have any questions? Well, this is a conclusion of things that I learned, learning outcomes, and then my future work is sort of, I'm going to optimize the geometric structure of the manipulator using a weighting factor. So then you can say what kind of characteristics you want of the manipulator and optimize its geometric structure to achieve that.
Yeah.
Questions?
What's the benefits of having the actuators in the base structure rather than in the joints and arm?
Yeah, so they're all here. So when you have the actuators here, it's really heavy. So this actuator has the lift around this one. And there's two here and two here. So having them in the base allows you to minimize the length to diameter ratio. You can make the diameter smaller because you don't have the actuators, big actuators in there which have to lift the weight distributed away from all the other actuators. Yeah.
When you're doing your tip positioning control, can you input your path constraints for this really complex path you already put it in to get to that point?
So that's called like obstacle avoidance, where you have to say where the obstacle is. You have to have a predefined obstacle to be able to implement that. So the way I get around that is using the tip following, where you don't have to have these predefined obstacles. You can just say where you want the end effector to go, and you kind of, assuming there's not too much error, you can assume that the rest of the arm isn't going to collide with any of the obstacles. Yeah.
One last question. Any other question? Yeah. Thank you.